Hello and welcome to the podcast for the Project B Week 4 seminar. Today's podcast will be introducing you to mass balance equations, which you'll be needing to know for your PIR and to help in your overall project. So before we get started, I'd like to introduce you to a reference text that if you go on to do chemical engineering that you'll use in second year called Felder's Elementary Principles to Chemical Engineering. So if you get stuck at any stage doing your mass balances for the project, this is an excellent text to refer to. So let's get in and look at how we do mass balances. So we look at the processes, and we can have a number of different types of processes. We can have batch, continuous or semi-batch. However, when we look at our first one here, we'll be looking at a batch process. So what do we mean by a batch process? So we've got a cooking pot here and it's got a system boundary, and this is going to be our batch system. So we've got a whole heap of ingredients that go into the cooking pot. Once we put them into the cooking pot, we seal the lid, and it is a sealed batch process, and we don't have anything crossing the system boundary. Once everything is cooked, the process is complete, and then we have our lovely spaghetti dinner from our batch process. So let's have a look at a continuous system. So in a continuous system, as you can see here, we've got an open tap running water into the tank, but then the tank's tap is also open, allowing water to be released. So in a continuous system, you continuously have inflows and you continuously have outflows, very basically. So we're going to have a look at a semi-batch system now. So if we have a look at the kettle has a system boundary around it, and the water that's boiling within the kettle is a batch system. However, while that batch system is bubbling away, boiling away, we're releasing steam through the spout, and that's crossing our system boundary, and that steam will continuously be released during the whole process. So this is a semi-batch / continuous system. So let's have a look how this translates into having a steady state or an unsteady state. So what does that mean? So let's have a look at the graph and use the graph to help us understand steady state versus unsteady state. So if you look at the graph, we've got an unsteady state system where the system is moving in a linear direction. So our mass is changing with time. And so that means that our state is unsteady. However, if we were to have a steady state system, and you can see this at the top of the graph, where we've plateaued out, our mass remains the same as our time is changing. So there is no change in mass over the change in time. So let's go now and tackle a problem and see how this will work. So we're going to have a look at a calculation where we have 100 grams of wet sugar, and we're going to put this wet sugar through an evaporator to dry the sugar out. So when we're looking at this, we know that from our problem definition that we have in our sugar, it's 1/5 of water that's making it wet. And then our evaporator can drive off 85% of that water out of the sugar. So before we get started and do a hand calculation, which I'll show you in just a moment, we're going to look at the general equation for mass balances, which is in minus out plus generation minus consumption equals accumulation. So let's move on and solve the equation in the previous slide. So the first thing that we want to do is define our system and draw where our evaporator is going to be. Okay, so this box is going to represent our evaporator. And it's always good to label all of your boxes and lines. Then we're going to have an inflow, and this is stream 1. And then we have 2 outflows, stream 2 and stream 3. And then we're going to label these streams. So we've got M1, XW1, XS1, and then we're going to have up here M2, and we'll put XW2 down here and XS2 here, and then we're going to have M3, XW3 and XS3. And then we're going to do a legend, and we'll come back and fill in some information here in a moment, but we'll do our legend over here just so we know what all of these terms mean. So M is equal to mass, W is equal to water, S is equal to sugar, and X is equal to the mass fraction. Okay, so let's see what information we can put in over here. So we know that our mass N is going to be 100 grams of wet sugar. So that's what this is here, that's 100 grams. And then we know by our problem definition that the mass of wet sugar is 1/5 water. So we know that that will equate to this being 0.2 mass fraction of water, and then the mass fraction of sugar will be 0.8. So the next thing that we need to do is actually state what our mass balance equation is. So I'm going to write that up here for you now. So the general mass balance equation is in minus out plus generation minus consumption is equal to accumulation. And then we're going to make a list of assumptions. And these assumptions will help us solve our equation. So, first up, our first assumption, number 1, is that our system is at steady state. And this is going to translate to accumulation being equal to 0. So let's get rid of that term. Our next assumption is that there's no reaction. So this is going to mean that generation is equal to 0 and that consumption is also equal to 0. So let's get rid of those terms. And this simplifies our equation to in minus out equals 0. Next, assumption is that our inflow has only sugar and water. And finally, in our fourth assumption, we're going to say that the vapour does not contain sugar. So this will mean that XS2 is equal to 0. Okay, so let's move on to doing the calculations, and you'll see that I've moved our legend over a little bit to give us a bit more room, and I've simplified our mass balance equation to in equals out, and we'll keep that up the top there. So we're going to go and have a look at stream 1 first. So let's write that in. Stream 1. Alrighty, so in stream 1 we have got MS1 is going to be equal to XS1 times M1, and we know that this is equal to 0.8 and this is equal to 100 grams. So that's nice and easy. That equals 80 grams. Then we're going to look at MW1, and again we know that this is equal to 0.2 times 100 grams, which is equal to 20 grams. You might say I've left out a section there, but this is your XW1 and this is your your M1, just in case you forgot what they were. Alrighty, let's move to stream 2 now. Okay, in stream 2 we already know that XS2 is equal to 0, which means MS2 is equal to 0. So let's go on to NW2. MW2 is going to be equal to, now this was something in our problem definition that said that the evaporator is capable of taking 85% of the water out of the in-stream. So we know that that's going to be 0.85, and then that's going to be times MW1, so the amount of water that's coming in our stream 1. So that's going to be equal to 0.85 times 20 grams, which equals 17 grams. So now we're going to go up to stream 3. I'm just going to quickly jump down here too, and we look at M2, considering that there is no sugar stream. M2 is going to be equal to NW2, which equals the 17 grams also, just in case you forgot that part. So let's do stream 3 now. So we know that our in equals out. So if we go to MW1 is going to equal MW2 plus MW3, and we're going to rearrange that to solve for MW3. So let's go MW3 is going to be equal to MW1 minus MW2, which is equal to 20 grams minus 17 grams, which equals 3 grams. That's for MW3. Now let's look at the sugar stream. So MS1 is equal to MS2 plus MS3. We know that that's equal to 0. So MS1 is equal to MS3, which is equal to 80 grams. So let's finally do the overall mass balance, where we have M1 is equal to M2 plus M3. So if we go here and then rearrange for M3, because we know M2 is 17 grams and M1 was 100 grams, let's go M3 is equal to M1 minus M2, and because we're running out of room I'm going to go out the side here, so that's going to be 100 grams minus 17 grams, which is equal to 83 grams. And if you have a quick look back, we could come to that quite quickly as well when we have a look at the fact that we've got the 3 grams there and the 80 grams there. You could also add those two factors to get your 83 grams as well, because they are the two components of the third stream. So that's our answer for our mass balance on this equation. If you have any more questions, we can answer them during the seminar. So, in summary, we can have three types of processes. We can have batch, we can have continuous, or we can have semi-batch. We can have steady-state systems and we have unsteady-state systems. And then we can have our general mass balance equation, which will help us determine what our streams will be going in and coming out of our system, which that general equation is in minus out plus generation minus consumption equals accumulation. So, questions to consider for your own PIR and for your project overall. Is my design batch or continuous? Is my design steady state or unsteady state? What assumptions can I make about my system so it will help me to come up with my stream balances? And why have I made those assumptions? Can I justify why I've made those assumptions? So hopefully this will give you a good start for our seminar on Monday afternoon. Thank you.